My name's Dave Langer. I'm going to make an assumption that you're not familiar with me and my content for this presentation, and if you are, please forgive me. So I am a YouTuber. I have a YouTube channel, and I'm a LinkedIn enthusiast. So a lot of folks know me from my LinkedIn posts in particular. I also got a website, so if you like what you see today, if you don't think I'm crazy, you can check out more of my content either on my website, YouTube, or LinkedIn. So let's talk briefly about me. As I mentioned to one of the attendees earlier, I do have a slide about myself. So to give you some background, I've been in technology a long time, more than 25 years. My first job was coding COBOL on an IBM mainframe, and that'll be relevant later on a later slide. These days, I am a independent consultant and trainer, as was mentioned earlier, through my company called Dave on Data. I've successfully trained hundreds and hundreds of professionals in a live classroom setting from all kinds of backgrounds, teaching them how to do data analysis and R programming and machine learning and all those sorts of things, and many thousands more via my online courses and tutorials. But more importantly for you guys today is I'm a hands-on analytics professional. I do analytics myself. Yes, I teach. That's a big focus of what I do, but I also deliver actual hands-on analytics work. And before doing that at Dave on Data, I was the VP of analytics at a company called Schedulicity. I spent 8 years in Microsoft, including working in the SQL Server team. And I've taught hundreds of professionals in a live classroom setting in my time at Data Science Dojo and with my partnership with TDWI at national conferences here in the United States when we have those these days. But most importantly for this particular topic today, I deliver machine learning projects for my clients. I'm in the middle of a project right now, delivering a project for a client, and everything that you're going to hear today is applicable to what I'm doing right now, as well as everything I've done in the past. Now, I need to ask you for some forgiveness because I get really excited about analytics, and I've been described as having a hand flapping communication style, so I'll be moving around a lot. So hopefully you're not going to find that too offensive because I love this topic, so I get really excited about it. Okay, so that's enough about me. Let's get going. What is the first thing that we should know about delivering machine learning projects in the real world for business customers? And like I said, this is all based on my hands-on experience over a number of years. And the first is keep it simple, right? Start simple. A lot of the stuff that you're going to hear in this presentation today might go counter to the kind of hype that you would see like on the LinkedIn feed or maybe on blogs or Forbes or whatever it might be. I'm going to give you my perspective of what it really means in the real world. And here's a shocking statistic for you. 85% of AI and machine learning projects fail. And you can grab more information here from this link if you're interested. I didn't make this up. And here's an excerpt from this article that I think is super important and really distills down why so many AI and machine learning projects fail. If you don't know what question you're trying to answer, what what business question are you trying to answer with machine learning or AI, call it what it should like, it's a recipe for disappointment. And by the way, this is true not only for machine learning, but it's also true for any sort of analytics that you're doing. You need a good business question. So you need essentially a well-framed business problem to tackle. And a lot of folks just these days aren't doing it. A lot of managers are like, hey, look, I've read about AI in CIO magazine and I need AI. And you go off and you do something and it doesn't necessarily generate value. If you have a very simple, specific question, that is going to help you up the chances that you're going to be successful dramatically. So most of the machine learning models that I've built for my employers and for my clients are simple. They're binary classifiers, right? Can you predict a label, yes or no? And it turns out that this simple machine learning model is broadly applicable and is a great way to combat this idea right here, which is if you don't have a well-defined business question, you're likely to fail. Let me give you some examples. So HR, will this employee quit soon? That's a binary classification problem. Product management, will this SaaS customer be sticky, right? Are they going to subscribe to our software as a service and keep paying us month over month? Will this customer churn and will this lead convert? Is this warranty claim fraudulent? Will this incident escalate? Now notice that all of these are very simple questions, and they are quite valuable. Just about every business or every client that I've ever worked for or consulted with have all these questions, and at various levels they don't have good answers to them. This is a great area for practical machine learning. Start simple. Identify these simple binary questions. Don't go off and build a cat video classifier or something like that. Not that that's not valuable for somebody like YouTube, but in the vast majority of situations, especially in large organizations, Fortune 1000 corporations, US governmental agencies, those kinds of types of organizations, you'd be surprised at how often these simple questions give you a chance to prove value of machine learning and up the chances that you're going to have a successful project. Now, one of the things that I also want to mention as well is beware this myth. Be wary of the myth that only production machine learning models are valuable. They certainly are. Don't get me wrong. I'm working on a project right now to put a machine learning model in production. There's value in that. However, you need to understand that machine learning can also be used as a data analysis technique. So for example, you might even conduct a data analysis via machine learning model to answer one of these questions, and you never might put that model in production, but you might use the results of that machine learning, for example, in a data story that you present to an executive, and that drives change. That makes the machine learning model valuable, even though it didn't go into production. So I just want to make sure that I'm clear. Yes, production machine learning models are valuable. They absolutely are. But two, they're not the only way machine learning models can bring value to a business. So essentially, never underestimate data analysis, whether using machine learning or not. Okay. So here's the first takeaway. Break the cycle. Please break this cycle. Find a simple but valuable business question and tackle it. And by the way, you don't need to wait till the end of the presentation here, the talk, to ask me questions. Feel free to ask questions at any time. I'm going to go ahead and try and monitor the chat a little bit as we progress in case there's a question, and I will answer it as we go along. Okay, keep things simple. All right, next up. Okay, so forgive me. If you're going to do a presentation about machine learning and you talk about data, you got to put a matrix style representation of data in your slide deck. That's my opinion, right? So here's data, matrix style. So if you're going to do machine learning or analytics of any form, but especially if you're going to do machine learning in the business space, if you're going to apply it either in the production context or in the data analysis context, you better love data. You better love working with data. So to really emphasize this point, let me give you another stat here. Generally speaking, based on surveys here, you spend about 14% of your time actually doing modeling in a predictive analytics project. 14%. So if you have a 100-hour project, you're doing modeling 14 hours. So I would argue that this is pretty valid based on my experience. This maps totally with what I do with my clients and with my previous employers. But I would argue that my experience is a little bit more optimistic, a little bit more cool than that. It's about 20%. It's about 1 out of 5 hours. And I'll talk more about this later on when I walk you through a hypothetical workflow that I use, where modeling is part of an exploratory process, which ups that percentage from 14 to 20%. So, I mean, here's the reality. And if a lot of you are in IT or in data that are on the call, this is going to sound very familiar to you, which is, what do you actually spend 80%, 86%, maybe even 90% of your time doing, depending on the nature of the project? Well, it's all the things that you might hear people complain about or might be well known to you based on your own experience, which is you go to meetings. As much as you would just like to sit at your desk or at your laptop at home and just work with data and model and do code, you still got to go to meetings. It takes up time. Getting access to data is a problem a lot of times in a lot of companies. For example, I'm a consultant, so obviously when I go in, I need to get special access as a consultant to data sources. But even when I worked at Microsoft as an internal employee, as a blue badge, I didn't have access to all the data. I had to go to different orgs and different teams and request access and go through the process, and it was a pain. It took time. It's a lot of time just to actually get access to data, especially in large organizations. Now, of course, you're going to spend a lot of time exploring and understanding the data. You got to do that. There's no magic around that. Things like AutoML are super useful, but even then, there are limitations with what they can do with raw data, especially coming from transactional systems or data warehouses, for example. A lot of times the data is just not in a state where you can just feed it to an AutoML system and it's going to deep fry your data and awesomeness is going to come out. Look at IBM Watson, for example, as a point in fact. So what ends up happening a lot of times is when you're going through this process of exploring and understanding data, you get questions, right? Because if you're not intimately familiar with that particular database table or that particular log file or whatever data source it might be, CSV, Excel workbook, whatever it might be, you got to go ask somebody who knows about the data something about it so that you can learn it if you're not an expert. And generally speaking, if you're doing this work, you're going to be not working on the same database over and over and over again, usually, for example, or the same data sets. You're going to be moving around, looking at new data systems, new sources, that sort of thing. So there's always going to be questions, and you don't get those questions answered right away. So you got to wait. So that takes time. Then, of course, you've got the normal stuff you would expect. You got to clean the data, you got to wrangle the data, it's feature engineering, all the kinds of things that you need to do. And then typically what ends up happening is you got to explore the data again, and then eventually you got to rinse and repeat. So you go through this process over and over and over and over again. Now, the reason why I'm laboring this is because if you're on the call and you're interested in moving into predictive analytics or data science or whatever as a full-time job, then you need to know if you do not enjoy this process, which is like 80+% of the work, then analytics might not be for you, right? Maybe data engineering is more interesting to you, or software engineering, for example. You know, folks, there are folks that do not necessarily enjoy this process in of itself. They just want to model all the time. And that just doesn't work. It's not the reality of the situation. You've got to love this process if you're going to do this for a living. Now, I do need to make mention an aside, and for those of you that are familiar with my content, this is not going to surprise you at all. SQL, structured query language, is still the single most valuable skill if you're interested in applying machine learning to business. And the reasons for this are pretty simple, right? Every popular data storage technology in widespread use has a SQL interface. And for example, most large organizations, Fortune 1000 companies, governmental agencies in the United States, for example, they still rely very, very heavily on relational database technologies like PostgreSQL, Oracle's Microsoft SQL Server, IBM DB2 on a mainframe, all these sorts of things. So SQL is still the single most valuable skill that you can have because you're going to use it all the time in this process. So if you don't got SQL and you're interested in getting into this space, be sure to learn it. It's actually more important than learning the machine learning algorithms, believe it or not, because you spend 80% of your time working SQL. All right, I'm going to pause and see if there's any questions in the chat. Does not look like it. All right, so I'm going to go ahead and move on. Gotta love data. All right, cool. Next up, time. And I don't want to get all like Stephen Hawking on you here or anything like that, but time is arguably the single most important concept in applying machine learning to business, in my experience. And unfortunately, this isn't really talked a lot about. It's not talked a lot about in online courses or on LinkedIn. I'm guilty of this as anybody. Maybe I should start making some posts on this, by the way, on LinkedIn, that it's not really covered. So if you're taking my advice and you're like, okay, Dave advised me to go find a simple but valuable business question first and foremost. All right, I'm going to go do that first. I love data. That's the second thing. The third thing is you need to ask yourself, how does time impact my project? Because that's going to help you break that cycle of like 85% of projects fail, because time is almost always involved in some shape or form. So let me give you some examples because this is pretty abstract. So I want to talk a little bit about specific examples from my own work here. So first up, how are predictions going to integrate into the business process? Because that's a time-based question in reality. So for example, if you are building a model, let's say you work for a bank and you're building a model for approving or denying based on a web form, a loan application, let's say. I'm making this up. If you're familiar with underwriting, don't freak out. This is a hypothetical example. So someone comes to the website, they fill out a bunch of information, maybe they upload some documents and all of that, and your machine learning model is designed to predict whether or not they can get an approval right then. Right. And maybe if they get a no, it gets kicked into underwriting for a lengthier process. The time aspect is like, okay, I would expect a sub-second kind of response, ideally. So I've typed in, as the user, I've typed in all this stuff and I hit submit. I would expect an approval relatively quickly, right? So what that means is that time-based element is going to dictate how my machine learning solution is going to look. It might be some sort of API that needs to be integrated so the website can call it in real time. Right? I need a like a REST endpoint or something like that to call that model and say, hey, Dave applied, yes or no, should we approve him? And then it comes back. So that's the time aspect. Something that isn't talked a lot about these days, but which is actually more important, I would argue, is a lot of times what you're doing is you're integrating your machine learning models, the predictions, into human-centric business processes, which are usually inherently batch. They're not real time. So for example, imagine that your that same application for the bank is now somebody fills out their form online, they hit submit, and then they get a web page that says, okay, we've submitted your application. You're going to get a response within 24 hours. Because let's say behind the scenes, your business process actually is you're going to go ahead and generate a prediction for that loan application, but then send it to an underwriter for final review, human in the loop kinds of things, right? And this happens all the time. Sometimes it happens because that's just the way the business decides they want to work. And sometimes it's because of the law, because of the regulations require that. So you have to have a human in the loop. You still want the prediction because maybe the underwriter looks at it and says, oh, the model predicts 99% that we should apply this, approve this. I'm totally cool. Go approve it. But notice that that batch-based process now says, look, I don't need to build an API. I can build a much simpler solution based on some sort of batch cycle. So think about the timing of the business process, and that will determine how you actually deploy and use the machine learning model in practice. And once again, you want to use the simplest thing that will work for the business. And oftentimes that's actually batch. It's not an API. It's not something real time. Now here's another one, and this goes back to the mainframe thing I was talking about earlier. Oftentimes, when you're building a machine learning model, you're relying on upstream data sources that are inherently time limited. Classic example are mainframes. Many large organizations and governments, corporations and governments have mainframe systems. I spoke recently to a very large retailer about potentially doing some SQL training for them. And when they found out that I used to write COBOL back in the day, they're like, hey, we have tons of COBOL still running. When we can't find COBOL programmers, do you want a job? What I'm trying to tell you is that modern large organizations still have these upstream systems that operate on a different time cycle. So your solutions are often limited by that. You can't build a real-time predictive model if some of the data that you're relying on is coming from a batch-based mainframe system, for example. So that's another thing to take in consideration. And lastly, and maybe most germane for this particular talk today, is how does time, the concept, map to the attributes or the behaviors of what I'm trying to predict? So another way of saying this is number 3 here is all about creating time-based features for your models. And I'm going to talk more about that in a subsequent slide to really cement it. But this idea of like even the features that I create using SQL or R or Python or whatever you're using might actually have a time component. And in fact, that's actually really common in my experience. So I'll pause, see if there's any questions so far before we move on. Nope, looks like everybody's okay. Sweet. Okay, so I want to talk a little bit about data splitting, right? This is the next thing that I need to talk about from a real world trenches perspective. So we've talked about keep it simple. We've talked about time. We've talked about you got to love data. And now we got to talk about some of the practice here of machine learning, which is you got to split your data. So if you're familiar at all with machine learning, you know that the data is the raw material, right? This is what you start with. This is what you learn the patterns from in your predictive model. Now you want to make sure that your model is awesome, that in fact it works. So you actually need to test it to make sure that it's going to function well in production. So the first thing that you do is you split your data. This is a real simple way that you do it. You take some of your data and you say, look, this is what I'm going to use to train my model. And then I got some data over here that I'm used to test it. Now, this is the practice part right here. So everybody knows, anybody who's familiar with machine learning at all knows this, right? Your training data is what you use to build your model. And that's usually an iterative process, right? Use like something like cross-validation, for example. You build some features, you run it, check it out, you see how it's going, you tune the model, all that kind of stuff. So you're iterating through that training data many times. Now, the problem is that you can make your model too good for the training data, and then it becomes useless for any other new data that comes down the pike, which is why you have this thing called the test holdout. Now, here's the key, though, and I see this happen over and over again, and this is the law, and it's very simple. When you segment out your test data, you need to pretend like you're giving it to a security company and they're throwing it in a safe and they're closing that safe and you can't get access to it because you can only use this data once and only once. And it is so tempting. People are so tempted to break this cardinal rule, but it is the law. You can only use this data once and only once. And this is super important because what you're going to do is use this data to verify whether or not your model is actually going to meet any sort of business requirements that you have. And if you use it more than once, you pollute it. You don't actually know for sure. You have no way of estimating how good your model is. So you can only use this data once. And I know that sounds very simple, but it is so tempting to use it more than once. Can't. Nope. Don't do it. So that's the law, right? Learn it, love it, live it, hold it near and dear to your heart. It as tempting as it might be. For example, you might get business partners or customers or stakeholders, whatever you want to call them. And I've had this happen to me where they're like, well, can't we just like tweak the model and then run it through the test set again? No, no, you can't. And you got to stand firm on that. So that is the law. Now, inevitably, when people ask me, or I talk to them about data splitting, inevitably they ask me like, okay, that's great, Dave, I get it. But how big are these boxes? Now, they're not drawn to scale, okay? Just so you know, they're not drawn to scale. But typical questions that I get are, well, what percentage split should I use, Dave? Obviously, the more data I have from my training, the better off I am. But I don't want to shortchange my test set either because I want to make sure that it's a good test. And what I can see is like I often get asked, hey, is it 80%, 20, 80%? Is it an 80-20 split? Is it a 70-30, 60-40? What should it be? And the answer, unfortunately, is um, it depends. That's the real answer to the question is it depends. And people get, and justifiably slow, so they get a little frustrated with that. But here is the reason why it depends. The guiding principle is that your test data set needs to be representative, which makes some sense, right? If the idea is that your test data is your final check to say, look, is my business requirement going to be met, right? Well, this model accurately predict things with new data coming in, then I need the test data set to be as representative of all the different permutations of what could happen in the future as much as possible. So that's why you can never actually know for sure what's going on. Okay, so got a great question. So Lars asked, test data, is that per model? And the answer is yes, generally speaking. Now, the reason why I'm hesitating is because typically what you're going to do is you're going to use what's known as use something that's known as an ensemble, which is a particular algorithm that takes many models and blends them together for you automatically. For example, the random forest or a boosted decision tree. So If you think of the ensemble as a single model, then the answer is yes. It is, the test data is used for your single ensemble that you want to test at the very end of your project to be sure that if you put the model in production or if you use it for business decision making somehow, that it's going to be accurate. Now, your training data here will actually be used for many, many models because you might create ensemble version 1 and then say, ooh, that's not very good. I'm going to create ensemble version 2. That's better. And then 3 and 4 and so on and so forth. So from that perspective, your training data is often associated with multiple models. So Lars, let me know if that answers your question. If not, go ahead and follow up with another question in the chat. Okay. Oop, got another question from Joshua here. Let's see. Question, would you need to calculate power to identify the necessary sample size for the test data, or is there other ways to calculate the optimal number of test data set? Okay. So Joshua, I'm assuming you're referring to statistical power, for example, understanding, what's your 1 minus beta for like a A/B test, a t-test, that sort of thing. And strictly speaking, the answer is no, not in the machine learning world, because these are non-parametric non-parametric techniques, excuse me. They're algorithmic. So for example, you cannot represent a collection of decision trees like in a random forest or in an XGBoost boosted decision tree model as a single equation. So no, it's a qualitative exercise. And generally speaking, what you're going to want to do is, again, you're not supposed to look at the test data, right? Except for the very end of the project. So what you have to do is you have to kind of take a look at your training data, for example, and say, I'm going to go with a small test split first. Let's say maybe like 90-10. Don't look at that 10%, let's say, and then do the training data, do a random sample of the training data, and then say, okay, how representative of all the various permutations I have. So it's a qualitative iterative exercise rather than a mathematical one. That's a great question. By the way, just for if any of you have formal statistical backgrounds here, you might find some of this heretical, to be honest with you, because quite frankly, a lot of this stuff doesn't necessarily apply all that much in practice, to be absolutely honest with you. Okay. So as promised, time is one of the most important things in applied machine learning. So time, even the concept of time even affects your data splitting. And to Joshua's question, this is another example of where you see some divergence between classical statistical techniques that are applied in a scientific context versus what you often see in machine learning, you know, panel data notwithstanding, that sort of thing, which is time matters oftentimes in your data. So it affects your data splits. So I'm going to present to you a place where I typically start in my projects. It's not always guaranteed to work. The percentages are often altered based on the nature of the situation at hand, but it is a reasonable heuristic, a reasonable rule of thumb of some place to get started. So this is how we change up our data split based on time. Usually what you want to do is train your models on your oldest data. And the reason for that is simple. It's because businesses change over time. I mean, we've gone through a huge change in the past couple of years, right? 2019, everything was probably pretty close to, historical trends and patterns and that sort of thing. And then 2020, whoa, COVID hit. And then for a lot of businesses, for a lot of business processes, things changed radically. So if you want to build a predictive model that works in the COVID time period, for example, you need to understand that things have changed. So if you want to find the underlying transcendent truth in the data, you need to use the old stuff. Because if you find the old stuff that accurately predicts the newest stuff, you're golden. You found the transcendent underlying truth in the data, the patterns that matter, the patterns that work, the patterns that you can use going forward in your decision making or your production system. So typically this is what you want to do, right? You want to do some sort of split. Now I throw a dedicated validation set in there. That's just me. That's just the way I roll. and it's about 5% of the data. So what ends up happening is that you have this kind of tiered structure. So this is the newest 20% of your data. That's your test holdout set. Remember, it's the law. You don't get to use that for anything. You get to use it once at the end of your project, and that's it. That doesn't change. The validation is a nice small set, and 5% is just a rough order of magnitude estimate. Once again, it's all about this qualitative idea of, is the data representative? If 5% is representative of all the permutations that you can see in the test set or in the future, then that's good. That's all you need. Maybe you need a little bit more. Maybe you need 8% or 10%. You'll need to figure that out. But what ends up happening is that you iterate over here, right, on the 75% of your oldest data, and you get better and better and better. And you spend a lot of time there, right? Engineering features, exploring data, tuning models, all that kind of jazz. And then periodically, maybe every project milestone, maybe every couple of iterations of the feature data cleaning, tuning effort, you go run it against the validation data just to make sure that things still look good. And then you do this process iteratively until eventually you reach the end of the project. And then, and only then, do you use the newest 20% of the data on to validate your model to make sure that it's actually good to go. Okay, we got a question from Nikita. What is the difference between validation and test data? It's a good question. And the answer is it's semantics, essentially. It's how the data is used. So test data is used once at the end of your project to validate that your model's predictions are actually good, that they're going to be meeting the business requirements once the model is used in a production scenario on brand new data that it comes in that's never been seen before. So that's what the test data is. That's why you only use it once. It's the best you can do to evaluate whether or not your model will work well in production on brand new data that's never been seen before. So that's test. Validation is simply just another data set that you use periodically, every so often, maybe at the end of each major project milestone, to say, look, I've spent a lot of time tweaking and building my machine learning models over here, but I'm worried that maybe I'm overfitting to my data. I'm memorizing this data over here to my detriment. So this validation is a periodic check to say, have you focused too much over here? Or have you actually found the general patterns in the data, what I call the transcendent underlying truth in the data? And I'm going to do a periodic check to make sure that I haven't gone off the rails. That's basically the difference. It's a great question. So once again, and it bears repeating, in my experience, it's rare in practice for time to not be a factor in applying ML in the business world in one shape or form, whether that's your data splitting, the features that you engineer, how you're going to integrate in the business process, how your data comes to you from upstream systems. Time is everywhere in applied ML, in my experience. Okay. You guys are asking great questions. Thank you for that. So moving on. Next up, we got features. Okay. So applying machine learning in the business world is all about three things, right? First up, framing the business problem correctly. And we saw that earlier, right? That's not me talking. That's Gartner research tells you that, look, 85% of machine learning in AI projects fail, usually because they don't frame up a business problem that is tractable, that actually can be solved, is understood by the business, and the value can be easily quantified by the business. That's why they fail usually, is because that doesn't happen. Then you got to understand the data. Not surprisingly, right? You got to love data because you spend a lot of time, 80 to 86% of your time working with the data, the raw materials. And then lastly, it's all about feature engineering. This tends to be more important in my experience than anything else, the features, right? You got to have these first two things, these first two things, right? That's the foundation. But where the rubber meets the road in like terms of like hands-on machine learning types of activities, it's all about the feature engineering, because that's where the business knowledge meets the actual raw materials that gets fed into your machine learning model. So I'm going to give you a specific example of feature engineering if you're not familiar. And not surprisingly, based on what you've seen so far, I'm going to use this. Who knows what this is? Just type it in the chat. What this thing in dark blue is. Just put it in the, what is this thing right here? Our audience participation is always tricky. Okay, no one wants to respond. That's fine. It's a timestamp. This is literally what you might see, for example, in date and time. Thank you, Joshua. Thank you, sir. Appreciate it. This is literally what you would see, for example, when you go in, look at a database table, and you have a column in a database table that represents date and time. Or you might even see this in an Excel table, for example, as you might imagine. Now, here's the thing. Not surprisingly, I will tell you that one of the most useful of all data that you use in applied machine learning is a timestamp, because this offers you a wealth of feature engineering possibilities. So let me give you an example of what I mean by this. If you've never built a machine learning model before, or if you have, that's also cool too. But know this, never use this data as represented like this in your machine learning model, ever. Never, ever, ever, never, ever use this as a raw feature into a machine learning model. Because let me give you an example of why. I worked at Microsoft, as I told you, for a number of years, and I spent a number of years working in Microsoft's supply chain organization. We were responsible for building and distributing Xboxes and Xbox 360s and Kinects and Xbox One and all that kind of cool stuff. And we had we were interested in understanding, predicting whether or not a particular piece of hardware was going to have a failure, right? Xbox gets to someone's house and it breaks down. So we had a guy in my organization try to build a machine learning model to predict failure, and he put in the raw timestamps into his machine learning model, and his model was like 98% accurate. And he's like, Dave, this model is super accurate. This is so awesome, isn't it? And I said, whoa, wait a second. That's too good to be true. What's going on here? And the reason why his model was so accurate was because there were certain days where there were problems in the production line, or there was a batch of bad components that came in. So the individual dates were highly predictive because of that. So his model was awesomely accurate on his training data. So let me go back up a slide. His model was awesome on this. It was super perfect, accurate on this, like 97, 98%. And it would stink for anything else, because anytime a new date came in that wasn't in his training set, so let's say his data only went to the end of 2016, let's say, it would stink for dates in 2017 and 2018, so on and so forth. So never, ever, ever use a raw date timestamp in your machine learning. What you want to do is engineer this into a number of features, like so. So Khalid, I got your question. This is part of it right here, and I will answer more at the end of the slide. So look at this. This one piece of data, literally this is like one column in a database table, can spit out 1, 2, 3, 4, 5, 6, 7 features. And you can do this for every single date column that you have in your data set, because you might actually have multiple dates for different kinds of things, because once again, time matters. So you can engineer tons and tons of features. Now, here's one of the things that you need to consider from a feature engineering perspective, which is, why would I use July here instead of the number 7? And the answer is because a lot of machine learning algorithms, especially the ones that I will talk about in a subsequent slide, interpret numbers as numeric features as numbers. And the easiest way to think about this is, does it make sense to do math on the features? So for example, if you have, let's not use June as an example, let's use a different month. Let's say we have the month of April, right? April is the 4th month of the year. And we also, let's say, have August in there, which is the 8th month of the year. Does it make sense to say that August is twice as big as April? No, it doesn't, not arguably. So that might be a reason for you to engineer the feature as not a number, but as a categorical, right? July Is July any better than September? Is July any better than, you know, March? And the answer is no. Now you might be saying, well, yeah, but Dave, July is later in the year than March. That's okay. What you could do, which I didn't put in the slide for space reasons, is you could add another feature called quarter, right? Or month, month count or something like that, which actually would put them in kind of an order in terms of the timeline. So all that to say, when you're using features like this, you really need to think about what are the representations that I want to use. That's the essence of feature engineering. And you can see here, I can engineer a ton of features, and I can engineer even more features out of this that I did, that I didn't even put in because of space reasons, like quarter, that sort of thing. So just so that we're crystal clear, just to give you some sort of sense of scale here. In a project that I did last year for a client, I had a single database table that I was using as part of the project. There were other database tables, but I'm just going to use this one as an example. And it had 46 columns. And that included, by the way, a couple of ID columns, which you also don't use in your machine learning. So, it's a little less than 46. And I was able to engineer 330 something features out of that. Now, I didn't use all those features in the model, but that's the process, right? You start engineering all these features, you brainstorm, and you create all these features, and then you see which ones are actually useful in the models. Okay, so Khalid said, what are the steps and resources to master feature engineering? Okay, it's a great question. And the answer is, there is a certain level of science to feature engineering, but there's also a certain amount of art to it, which means that, at least so far, it means that Skynet is not going to take over the world yet. Humans still have a place in the process. There is a really good book. Let's see. Oh, I have a copy of it on my desk, but it's actually underneath my monitor right now, so I can't access it. There's a really good book by Max Kuhn. I'll type it in the chat here. Max Kuhn, he works for our studio. And you can search on Max Kuhn feature engineering in Google. And that's a really great book that will introduce you to the process of feature engineering. Awesome book. Now it uses R. There's also a feature engineering book that you can buy on Python. That's where I would start. You can also Google feature engineering and read blogs and articles, but this idea of how do I take a particular representation of data and break it into constituent elements that might embody a pattern that the machine learning algorithm can pick up. That's the essence of feature engineering, and those books can give you a lot more detail on how to do that. You're welcome. Okay, Nikita, do we also not use the timestamp for geospatial kind of analysis? You could. You certainly could. If I understand your question correctly, I have certainly done analyses where I used position, lat and longs, for example, to characterize the data. Now, depending on the nature of the business question that you're answering, you might also need time, because you might actually be like, not to scare anybody here, not to get all, big brother watching you, but if I need to track physical movement over time, I would need both geospatial and timestamp data to actually track that. Now, what I would want to do, though, is I wouldn't want to feed the exact timestamp into the machine learning model, because again, it'll tend to want to isolate on that particular piece of data to its detriment. What would be better is, for example, take Dave Langer's movement on January 1st, 2022. What would be better is to extrapolate that out into a generic count. So first timestamp, second timestamp, third timestamp, fourth timestamp, fifth timestamp. That would be better, because then as you went through all of your data sets, what you would do is you would genericize out the specific timestamps and say, okay, generally speaking, if all of my customers start within 5 feet of the door, around, at the very first visit to the store, and I'm totally making this up on the fly, that's highly predictive of them buying something, that kind of thing. But you wouldn't want to use the exact timestamp. Great question. Okay. Okay. Other thing that we need to be aware of is what's known as leakage. And I'm not going to drain this definition for you. It's mainly for the recording, so you can go back and look at it at your leisure. But information leakage, data leakage is one of the banes of machine learning because it's so easy to implement it as you're working through your machine learning models. And let me give you some specific examples here. So first up, the key ideas that this definition tells you in practice when you're actually building machine learning models in the business world is that any data or information, first and foremost, that is in the test set cannot bleed into, it cannot leak into your training data. Because if it does in any shape or form, that influences your model to understand about what's going on in the test set, which invalidates the test. Think about it this way. If you were at university and you got some high level information around what's about the test, your final exam at the end of the course, which is actually what happens, it helps you out, right? You often get from your professor an outline of what's going to be on the final exam, and that helps you study so that you can do better. That works in the university space, but you don't want that in machine learning. You want your model to be absolutely ignorant of what's going to be on the final exam. Absolutely ignorant. So just remember that. Okay. If nothing else, remember that final exam analogy. I don't want to be a nice professor. I don't want to be nice to my students. I want them to know absolutely nothing about what's going to be on the final exam. They need to learn everything from the training data that they need for the final exam. So with cross-validation, and we don't have time to go into cross-validation, but use it. Absolutely use it. Any data or information in the validation folds cannot be used in training. So again, we can't go into cross-validation due to time constraints here, but this idea is that each fold in your cross-validation set should be independent of all the others, because that way you're using a holdout fold as essentially as a mini test or validation set. So you can't have any information bleed through. And once again, it's this idea of, think of this as like a midterm at a university course. We don't want our students to know anything about the midterm. They need to learn everything from the training data to be fully prepared for the midterm. Once again, and that's what this is essentially, that's analogous to this, right? We need to make sure that our validation fold, our cross-validation folds don't bleed across each other. Otherwise, students know about the midterm, and we don't want that. So row-wise feature engineering, this is super important. Row-wise feature engineering does not violate 1 and 2. You're good to go. And let me go back a slide to just give you an example. This right here is row-wise feature engineering, right? Because notice that this is a timestamp from one row of data in a table, in a database or an Excel or whatever it might be. And I've just expanded out for that row, the year, the month of the year, the day of the month, all those sorts of things. This does not violate rules 1 and 2. So you have no information leakage. So if you focus primarily as much as you can on row-wise feature engineering, you're good to go. You're going to avoid leakage. This is a good thing. Now, reflexively, column-wise feature engineering is actually a common way to violate this, right? Where you take, for example, the average of an entire column of data and you use that as a feature. That's a very good way to get leakage. Not surprisingly, those tend to be quite powerful predictive features because they leak data. That's why they're powerful, but you don't want that. Now, generally speaking, there are frameworks that can help you out to prevent this sort of leakage. So use them, things like tidy models. And lastly, take special care with time-based features. So if you do a time-based feature, make sure that it's only stuff that happens before the observation in question. We have somebody not on mute causing a lot of static. Okay, sweet. So for example, imagine if you're doing churn, you're trying to predict whether a customer is going to churn. What you would do in your feature engineering is you say, look, for each date in my data set where a particular customer churned, I need to make sure that my features only go from the day before backwards. And notice that that backwards feature engineering is going to be different for every customer because they all churn on different days. So make sure that you're aware of that, otherwise you're going to get leakage. So in essence, be super, super careful with all of your feature engineering. If not done correctly, you're going to produce models that are problematic. You're going to produce models that look awesome, but in practice are not. Okay, so moving on. This is where things get some heresy. I'm going to go through 4 slides of data visualization here. And what I'm going to assert right now is these 4 slides, when combined with one of the last slides, will show you that to be effective, to use machine learning to be effective in the business scenario, you can consider the knowledge of the way the mathematics of the algorithms and the actual implementation, the actual coding, the actual algorithm itself, you can consider them optional. You can actually build effective machine learning models, either for analysis or for production deployment, without actually knowing the underlying mathematics and algorithms. Now, don't before the haters start flaming me here, just so you know, if you're going to get a job as a data scientist, then you absolutely need to know those things because they're going to ask you about them. However, in practice, none of my clients ever ask me anything about how the algorithms actually work, just so you know. Okay, so first up, these 4 data visualizations are by far and away, excuse me, by far and away the most common that I use in my actual hands-on work. I do these all the time when I'm exploring data. So first up, I do a box plot. And what I'm looking for is clean separation. What we're looking for are decision boundaries, right? So for example, this one doesn't look very good. This comes from the famous Titanic data set. So we're trying to predict which Titanic passengers perished or survived. You can see here, these people did not survive and these people did. And we've got the age of the passenger. And what we can see here is there's not very good separation. That's good information for me. I could say, look, you know what, this feature based on this visualization doesn't separate my binary classification labels very well. So it might not be that great of a feature. So box plots are super useful as a first pass technique, but you don't use them in isolation. And the reason for that is on the next slide here. So this is a color-coded histogram, and it's the same thing. It's the same thing as we saw on the previous slide. It's the same data. So we got the passenger age along the x-axis, and then we have it color-coded by whether or not they survived here. This coral color versus this, teal kind of color. And notice this. What we're looking for when we're doing this is we're looking for clean separation of the labels, right? More coral or more teal, for example. But now what we're looking at, instead of what we saw in the box plot, like this idea of like cleanly separation, we're looking for squares. We're looking for rectangles where the rectangle is predominantly one color or another. And let me show you an example. These 2 rectangles right here are predominantly turquoise, predominantly survived. Now, a machine learning model can pick this out and say, look, even though the box plot doesn't look all that great from a prediction perspective, oh, I can use this piece of the data right here probably effectively in certain predictions. So now this data visualization tells you that age might actually be a useful feature to put in our predictive model. And this is going to be a recurring theme on the next 2 visualizations, this idea of I'm going to look at squares and I'm going to look at the volume of colors. If the volume of colors is overwhelmingly one and not the other inside of a square, it might be potentially useful as a predictive feature. So histograms, awesome. Use them all the time, color-coded like this. Next up, this is what's known as a scatter plot. And what you can see here now is I've got the same color coding, right? The orange and teal, excuse me, the coral and teal. I've got age along the x-axis and the average fare, the average price that a passenger paid for their ticket on the Titanic. And what we can see here is it's kind of a mixed bag. But there are certainly areas that you could see where there you could draw a square and they're predominantly one color or another. So that tells you that maybe these 2 features in conjunction being added to your model could be potentially predictive. Now, of course, the only way to know for sure is to try it out. But this is this is the whole reason, like what you're actually doing with this thought process, by the way, is actually intuitively implementing the mathematics and the algorithm of the machine learning technique. You're just not knowing, you just don't need to know the math in particular. But this is exactly how the math works in practice. It draws squares and says, hey, is in this square, is it more one color than another? Cool. And then it's useful. And then lastly, we got bar charts, right? These things are awesome. And notice what we're doing here is we're looking at multiple things simultaneously. We're looking at whether or not the person with the ticket had the title of Mr. or Mrs. or Master or Miss, whether they were a first class passenger, second class passenger, and a third class passenger. And then we've color coded things again. And once again, we see, wow, we see bars that are overwhelmingly one color or another. And that tells us that these particular features are very likely to be useful in a predictive model. So we should certainly try them out. Now, this is part of that process that I said earlier. You acquire the data, you clean the data, you massage the data, you explore the data. And these are the kinds of things that you're looking at when you're doing, for example, binary classification problem. If you're doing multi-class classification problem, it's basically the same thing. If these were 3 different types of classes or 4, you would do the same thing. Same idea. Okay. And now probably notice that we haven't really talked about machine learning algorithms yet, right? We've gone through a whole bunch of stuff and I hadn't talked once about a specific algorithm, a specific machine learning technique. Well, here's the slide to address that. So here's a bit of heresy for you. In all of my work over the years, I have never used anything other than decision tree based algorithms for a production classification model. Not deep neural networks, not logistic regression, not support vector machines, splines, all the sorts of things that you could, well, splines, not splines, scratch that one. Basically, anything for binary classification model or multi-classification models, I've only used tree-based algorithms. And the reason for that is, I'll get into it. So here's even more heresy. I don't expect that I ever will use anything other than trees and decision tree-based algorithms. And the reason for that is pretty simple. As we've seen, the feature engineering for trees is relatively straightforward, right? You brainstorm a feature that tries to cleanly separate the labels embodied in the colors that we saw in the previous slides and the visualization slides. And then you visualize the data, you look at it and see, does it actually work? Very intuitive to engineer a feature and then explore whether or not it's going to be potentially useful in a model. These things are perfect for exploratory modeling, and I'll talk a little bit more about that on the next slide. Tree-based ensembles are relatively easy to explain. Now, some people would tell you that like a random forest is actually a black box model, that it's actually not interpretable. Wrong, absolutely wrong. What you do is simple, and I've done this with many clients, which is you do what I showed earlier in the data visualizations, and you just show them that in one shape or form. So for example, you show them this graph and you say, hey, you know what? The machine learning model said that this title feature and the class of ticket are extremely important. And here's the reason why. And you just show them this, and that's enough explanation usually from the vast majority of stakeholders. Now, yes, there are certain industries where regulatory compliance requires a different level of stuff, but the vast majority of businesses, that's not the case. This works well enough to explain what's going on in the decision tree ensemble. And here's the thing. The last thing is probably most important of all. Tree-based ensembles, for example, XGBoost, which is a boosted decision tree ensemble, or the Mighty Random Forest, are state of the art when it comes to small tabular data. And generally speaking, not surprisingly, based on the kinds of questions that I talked about earlier, most of the time you're dealing with relatively small tabular data. You're not dealing with billions of rows. You're not dealing with hundreds of millions of rows usually of data. If you are, that's a different story. But then again, you're probably not keeping it simple if that's what your data set is. So I'm just going to emphasize this again, right? While knowing the underlying mathematics of decision trees is useful, it is completely optional to get started with. You can craft nice, effective decision tree based models without knowing Gini impurity or calculating or how the algorithm actually splits or how the algorithm optimizes for numeric features. You don't need to know any of that to start. You can just use the data visualizations. That's more than enough. Okay, last slide. As promised, here is a very common workflow that I use when I'm applying machine learning algorithms, especially decision tree machine learning algorithms in the business context, because I learn the data, I brainstorm features. And as I told you on an earlier slide, once you get a handle on feature engineering, it is ridiculously easy to generate a very large number of features to explore. Hundreds of them, easily, thousands depending on the nature of the data that you're working with. Very easily done, especially the row-based kind of thing. So what ends up happening is that you can create so many features that, exploring them, which is usually a good idea because you kind of want to understand what's going on behind the scenes in case you have to explain it to somebody. That requires a lot of time. You're not going to create 4 data visualizations for 1,000 features. That would just take forever. So what you typically do is you brainstorm features, you engineer the features, and then you do what I call exploratory modeling. And you use something like the random forest, which can actually give you a ranking of how important the features are. And then you can use that then to narrow down the list of features that you want to explore. And then you go do the kinds of data visualizations that I talked about. This is also commonly known as exploratory data analysis, or EDA. And I've made some notes of the kinds of things that I typically use hands-on to make this happen. Lots of SQL, all right? Tons and tons of SQL code. I typically do most of my feature engineering, quite frankly, in SQL inside the database for any number of reasons, not the least of which is performance. I want to use the power of the database. I also use a library in R called dplyr, and I use the Ranger package, which has a really cool implementation of the random forest algorithm to do this importance calculation for me. And then I use the mighty ggplot2, which is a data visualization library in R. The visualizations I showed earlier were all built in ggplot2. So I iterate through this, and then, after several iterations to, I think it was Nikita's earlier question, this is when I use the validation set. Maybe I do this 3 times, and then I test the model with the validation set and see how good it is. And then maybe I do it 3 more times and then use the validation set again. And then eventually this process ends when the business requirements are met, or what's more common is the time box for the training phase runs out, which is I might meet the business requirement relatively early on, but I'm going to keep going to see if I can do better than the business requirement. And then usually what ends up happening is I run out of time, because you want to time box your projects, because in the end, you never know up front whether or not you can build an effective machine learning model until you try it out, because you just don't know. You just can't eyeball a table of data in a database and go, yep, I can totally make a machine learning model for that. You don't know until you try. So to scope the project, you usually use a time box technique. And then lastly, assuming that your business requirements are met, you build a final model one last time, and then you use that test data one time and then evaluate it. And then you say, okay, if my model meets the business requirement on the test data, I have a reasonable, it's not a guarantee, but I have a reasonable assurance that the model that I've crafted will actually work in a production scenario. That was a whirlwind tour. It's a lot to cover in an hour, and I apologize if if maybe I tried to cram too much into the presentation. So you guys have been doing a good job of asking questions. I still have time, so we can do some more Q&A if people would like.
That was outstanding. Thank you so much, Dave, for putting this together.
My pleasure. Hopefully folks find it useful. That's the main thing.
Hi, Dave.
Hello.
Hi. So I'd like to take one question. Thanks for the presentation. By the way, it was very informative. So I would like to know what are the best business problems that you have solved so far, which you found very interesting, and if you can share some experience on that. I mean, your challenges and what did you learn from that? Thank you.
Yeah. So as I've said, most of the stuff that I've done ends up being in the binary classification space. There are some other things that I've done that are pretty interesting, but I didn't cover enough material in this particular talk to talk about those. So one of the things that I found most useful is marketing problems. So in particular, digital marketing problems. Companies are spending more and more money on digital marketing. So like Facebook ads, Google ads, doing webinars, content marketing using blogs or social media, all that kind of stuff. So companies are shifting their marketing spend from traditional media like magazines and TV and radio to digital formats. And that's awesome for data folks because there's a lot of data being collected there and you can do a lot of analysis. So one of the things that I've found most interesting and most useful was things like creating predictive models for understanding who's going to convert. Like, for example, if somebody clicks on a Facebook ad and then lands on our site, what are the characteristics of that particular journey that is highly associated, highly predictive of conversion? However that's defined, right? They give us an email address and sign up for our newsletter, or they buy something, whatever it might be. That one I found super useful because the marketing space is a great place to apply analytics all up because when you're successful, you're driving the top line. And executives love it when you're driving the top line, even more when you're cutting expenses. So marketing analytics is a great place, like conversion modeling. And the cool thing is, what I've found over and over again in my work is the types of features that I engineer in that particular space apply to all the others. Right? The techniques for building like time-based features works for churn prediction. It often works for fraud prediction as well. It covers a lot of different kinds of spaces. So that's a good place to start. Great question.
Thank you.
Oh, you're welcome. Okay, we got another question here. What are the best practice or checklist to be followed while deploying the model into a production region? Okay, that's a real complicated question. And to be honest with you, there isn't a 100%, it isn't 100% well defined yet. There's not like a standard book of knowledge that you can go to. What you can search for is ML ops. I'm going to put this in the chat. So ML ops stands for machine learning operations, and it's this idea of systematizing the knowledge of actually doing exactly what you're asking. Like how do we build scalable, reliable, repeatable ML production systems? So I would search for that. But at a high level, there are a few things that you want to check. One is you want to make sure that, of course, the model can be supported, which would be different than any other production system, right? Does it have monitoring? Does it have logging? Can it report errors to your IT ops folks so that they can actually go say, hey, wait, the machine learning model is broken in production. We need someone to go hot fix it or something like that. So you need those kinds of things, which are the same for any production system. You also, most importantly, want some way of tracking the effectiveness of your machine learning model predictions to account for what's known as drift. Because once you put a machine learning model in production, usually it's not continuously learning. It's actually a snapshot in a point of time. And its predictions usually what ends up happening is over time, the predictions actually decrease in quality. So you want some ability to monitor the model's predictions and then what actually happened. So then you can account for that. That's known as drift. So you want to be able to monitor for drift, and that will tell you maybe you need to refresh the machine learning model. So those are two of the most important things, but check out ML ops.